So, good. So, last week saw an introduction to the summer term, and then today we start actually with the content. So, the content is kind of organized hierarchically, so we will start with things that might be a little bit further away from what you think we were doing, but they all have a reason to be there. But to frame the whole thing of why we're now actually talking about some fundamentals in mathematical probability theory, I want to briefly again bring up the problem. So we start with, as we discussed last time, a statistical parametric map, which is kind of the neurocognitive imaging term for a map of statistics. So, for example, a T-map. So we just heard about the beta parameters and the beta parameter estimates. If you put a contrast vector on them and divide them by the standard deviation, essentially you get a map of T statistics. And from the T statistics, you would like to create a p-value, because we're doing classical statistics and we're interested in what actually these SPM or other software p-values mean. So who can briefly define for us what a p-value means? Exactly, very good. So if you think in terms of the T distribution, roughly like that, centered on 0, then what you just said refers to the following. So you observe this T statistic here, let's call that your T, and then you said the probability of observing this or more extreme value. And of course, in parametric or continuous random variables, the probability of observing exactly this is 0, but the probability of observing this or more extreme, this is then this probability here, which is called the p-value. And we will, at one point of the course, actually go a little bit more about test statistics and tests in general, and p-values, and also then p-values in a multiple testing scenario. For the moment and for the first half of the course, where we talk about random fields, this is essentially, we can finally deal with this notion of a p-value. Now, this is the case where you have a single t-value, for example, from a one-sample t-test. Now, the problem that we face with fMRI and statistical parametric maps in one dimension is that we have kind of a scenario like this. So on the x-axis here, this is supposed to be space. And on the y-axis, I don't know whether this is a useful representation, but it's a representation. We have t-values. So you should now think that wherever there's a stick here, that's a point in space, and these points in spaces are the voxels, and then of course the voxels in fMRI, they are arranged in 3D, and here we have just arranged things in 1D. And the stuff that we are going to deal with in the first part of this section is the question of how to analytically describe and create a null distribution over space and the t-values. So what we are not, so in principle, if we would just focus on a single t-value, we could say, okay, we have a kind of a t-distribution about each of these t-values, and then somehow we make sense of it. And we will see when we talk about t-fields that this is also what happens, but what happens even more is that we assign a null distribution over space. So to create this null distribution, which we of course need to assign p-values. So here we so for this thing we have a null distribution, which is the t distribution, to basically formulate a null distribution over space, and of course over the statistics that occupy the space. To do that, we have to look into random field theory. And the whole thing about these p-values, of course, is that they are called random field theory based p-values. So you see that's already in the name that we have to talk about random fields and random field theory. I will call the whole thing, I think it doesn't come up in the script this time so much, but it will come up later. The whole thing, that this idea of taking random field theory to assign p-values to statistical parametric maps in cognitive neuroimaging, which is kind of a long sentence, I will call the whole thing RFP, because I need a short thing to name it. So that's random field theory derived p-values, or whatever you want to read into that. Yeah. But as you can see also in this RFP acronym, the RF for random field is in there, so we have to talk about random fields. So how can one very intuitively, and you should not really try to understand this today, because we will spend a couple of weeks to talk about this, how can one grasp that maybe intuitively what's happening and pictorial. So what we're trying to do is to find or discuss and understand a probabilistic model that if you sample from it gives you something like this. Yeah, that's one sample from it. If you again sample from it, you might get something like this. Oops, you get something. So if you specify the model correctly, still not working. Hello. Yeah, and if you again sample from it, now I try to do something a little bit different. See whether that works. You might get something like this. Yeah. So what I've drawn here are essentially functions over space. They are not probability distributions. It's not something like this density here, but they are samples from it. So if you want the analogy on this, then if you draw a sample from this t distribution, you would draw something down here, right? So you get a single value. From the random field theory, you get a function over space. And this is and these functions over space, they will have an expected value at every location in space of 0, and then one can use this probability distribution over these functions over space, which you actually don't see in the figure, but you can use the analytical knowledge to then assign p-values to these t-values. So that's kind of and to all of the p-values, to all of the t-values. So that's the very basic motivation to now study random fields and learn about random fields. Yeah? Good. So then we have to talk about random fields. That's what I'm telling you. And the whole thing is called random field theory-based p-values. So it makes sense to talk about random fields. Actually, you will find in the cognitive neuroimaging tutorial literature that they often try to avoid to talk about random fields when explaining this, and then it gets kind of iffy because it's really at the heart of this, so one has to talk about it. So the first 3 to 4 sessions, I guess, will be devoted to essentially basics in random field theory, and we start with this today. So first, we have to talk about some mathematical probability theory, because random fields are defined in terms of the concepts from mathematical probability theory. So I can read you the definition of a random field now, but it's not really meaningful because we will have to talk about probability theory first. But I read it nevertheless. That's definition D1 on page 15 of your today's handout. A real valued random field on a domain S is a set of random variables XX on a probability space omega RP that is for each X in S. X from omega to R is a random variable. So that's kind of the definition of a random field, and it's a sensible definition, but it rests on you actually knowing what a mathematical random variable is. So this is why we have to first talk about some probability theory, and then once we have gotten that out of the way, we can talk about random fields, and specifically also to see things in action, Gaussian random fields. And once we have talked about these and have basic concepts, then we get closer to the stuff that is actually related to GLM fMRI, which are the notions of smoothness of a random field, smoothness of random fields and excursion sets. So this is what we will have to do. Then we will talk about other things. So then we will talk about how to measure volumina. So we will have to talk about something that I call volumetrics. And I think then we have to talk about excursion set features. So actually for these things, they shouldn't make any sense to you right now, but you will see that they are coming up. Excursion set feature distributions, and then, only then, we will talk about p-values again and multiple testing. And once we have done that, then we are ready for the SPM table, essentially. So that's roughly the outline of the next of the whole thing about random field theory, p-values. And as you see, the notion of p-values and then the SPM table will come at the end. So have some patience, enjoy everything on the way there, enjoy the scenery, and don't get crazy because you think this has nothing to do with brain imaging. It has. Believe me, you can trust me. I'm just doing this because of brain imaging. But there's also a lot to learn on the way there. Yeah, so that's the outline for the entire way from today to understanding what is written in the SPM table. And these sections here, so that's really a first stuff on random field theory. Good. That's the outline. That's our plan. Anything coming up? No. So let's finally get to business and start with probability theory once more. So of course, we discussed some probability theory previously. And as you might remember, I said, so we discussed this table with the joint probabilities and the conditional probabilities and the marginal probabilities. And we also discussed what a random variable is. And I said, so we are using a definition for random variables here, which is not really exact, but which will get us a long way. So a random variable is something that takes on random values. And this gets you essentially, it really gets you a long way. So it gets you, I think, through all of what they call machine learning. You can happily live with that definition. In modern machine learning, you don't even need this definition because they don't like probabilities anymore. They just do neural networks. Also, basic statistics, essentially, you can get through without diving further into probability theory. But unfortunately, understanding or getting an idea about stochastic processes and the generalization of stochastic processes, which are random fields, this thing starts to stop because you need to talk about many random variables and they need to be in some kind of conceptual continuum, and they need to be, and they have different aspects. So it doesn't help. So we have to talk about mathematical probability theory, which is kind of, once you learned probability first, then you can relearn probability again using the mathematical approach. So this mathematical approach to probability theory originates from the early 20th century. So Kolmogorov, 1933. Is kind of one of the origins of modern mathematical probability theory. It's not that he at this point invented everything, but he wrote up what was around for some time. And what's happening in mathematical probability theory is that it's heavily inspired by what is called measure theory. And measure theory is essentially the mathematical formalization and approach to deal with volumina and to deal with assigning the notion of a value, the notion of a volume to sets. So this is why probability theory, modern probability theory, is always called measure theoretic probability theory, if you want. And Kolmogorov points out in his book, it's a book, it's like 100 pages, points out many analogies between measure theory, which was also popularized or really made possible by Lebesgue's work on integration, which is a generalization of the Riemann integral. So it establishes this link. Actually, one doesn't need that much of measure theory when talking about mathematical probability theory, but it's nevertheless there. And of course, the whole thing is aiming for generality and abstractness and things that can be applied to many contexts. So what we're talking about today is fairly abstract, and by this I mean also fairly general, so you can apply it in many contexts. And it's the most important thing, however, to always note when talking about probability theory that it's a model. Yeah, it's a model. We don't know whether anything is random in the sense of probability theory. We don't know anything, but we have a mathematical model. With this mathematical model, we start today. So first we need to talk about the notion of a probability space. Because as you might remember, the concept of a random field is defined with respect to a probability space. And then we have to talk again about random variables and distributions, this time from a more mathematical perspective. And the reason for that is that random fields are collections of infinitely many random variables, so we better know what random variables are if we want to know what random fields are. And then, because random fields have certain characteristics like covariance functions, we also need to talk about expected value and covariance. And so what I'm trying, of course, to do is to focus on the main aspects and not go into all the mathematical details that you will find in books. There are very good books on mathematical probability theory. For example, Billingsley is a classic, as they say. There's a new book by Friedstedt and Gray, which is awesome. Rosenthal has like a first course, which is also great, and Shao has this mathematical statistics book that rests on the meta-theoretic approach to probability theory. So there are many good books, and if you any of these concepts that we discuss in the whole, maybe in the first section on random fields, you will also find everything of this on Wikipedia, and I actually recommend to look at the Wikipedia stuff because it's generally quite good. So, probability space. Now, after a long intro, but I think motivation is always helpful. At least I hope that. What is a probability space? A probability space is a very, very abstract and general model of a situation that involves randomness. It's a mathematical model. Yeah, it's something that we write down now on paper or here on this digital machine. It's nothing that is real. It's a model. Yeah. So relax. It's a model. And the other thing why you also should relax is that it's a mathematical system of axioms, if you want, that is there so that a lot of things downstream make sense. So it's constructed so that a lot of things that you don't know make sense. So you should also not go crazy about trying to understand everything just from the definition, these definitions and formulations. They make sense in the context of everything that follows downstream. They are not there to enlighten anyone or to make sense essentially on their own, so that one defines that and then goes home and says, we defined a probability space. It's hierarchical. Yeah, it's how you should write a text. You first define something, make clear what you mean, and then you struggle with these definitions so that everything until the end of the paper makes sense. Good. So relax. Okay, just relax. Just relax. Okay. So a probability space is a triple omega r p. Triple just means it's it consists of three things, has no further meaning, so you can't compute essentially with probability spaces or add probability space or something. Well, you can in some way, but so triple is just meaning there are three things. And then always the question is, what are these things? Three things. So omega is a set of what is called elementary outcomes. And these elementary outcomes are usually called omega. So that's a small omega, looks like a W, and omega is a set of these omega. So this is already fairly general. So omega can be a discrete set, so something like 1, 2, 3, 4, 5. That's a discrete set that is finite. It also can be a discrete infinite set, so like the natural numbers. But it can also be a continuous set if you want, like the real numbers, or a real vector space. Yeah. So in the abstract definition of a probability space, omega is just a set, so it can be anything. So that's fairly okay-ish to grasp. The biggest problem with the definition of a probability space comes next, which is the notion of a sigma algebra. Actually, I use this mathcal. Maybe I should use it here as well. So it's kind of a nice A. A is a sigma algebra. And then, of course, the question is, what is a sigma algebra? Well, a sigma algebra is a set with the following properties. Omega is in this nice A. So that says just that omega is a set in the sigma algebra. Maybe I should add at this point that the sigma algebra is a set of sets. So there are a lot of sets in this sigma algebra. It is closed under the formation of complements. If a set A is in this sigma algebra, then also the complement of A is in this. There's something missing actually. I see here there's a typo in the script. Then also AC, this is the complement of A, which is omega without A. Yeah, so that's the definition of a complement. So if you visualize this, if you're not quite clear on the notion of a complement, so if this whole thing is omega and this is R, then the complement of R is omega without A, so that's the rest here, if this is A. So that's a complement, and in the script after the omega there is this without a missing, and the reason for that is that actually this backslash, as you might know in LaTeX, is also a command, and this I missed there. Can you? Thank you. And this holds for all A in this sigma algebra, and then A is also closed under countable unions. So if A1, A2, and so on are in A, then also they're countable. Countable means infinitely many, but countable in the sense that of the natural numbers. So only as many as there are infinitely many natural numbers. You might know that there are more real numbers than natural numbers, although there are also infinitely many natural numbers. So countable means infinitely many, but still countable from the perspective of the natural number are also in A. So this is kind of the worst thing of the whole course, this definition of a sigma algebra, because at this point you have no idea why we talk about it. I will make it clear with an example in a second, but really the sigma algebra is the most annoying thing in the whole measure theoretic probability theory from my perspective, because what you actually want, what you really, really want, is the power set. But the power set, so the set of all subsets, but the power set doesn't really work. So you have to deal with this sigma algebra, which is kind of a little bit smaller than the power set. We will come to that for an interpretation of the sigma algebra in a second. Finally, let's finish the definition of the probability space. So what is P? P is what is called a probability measure. So this gets closer to what you actually expect. So P is a set function measure. So P is a function from the sigma algebra to the interval 0, 1. And with the interval 0, 1, of course, one represents something that has the intuitive notion of a probability. So the probability measure, when it's 0, then it's essentially impossible. If the probability measure is 1, then it's happening for sure. So this is where this is coming from. But be aware that this P is defined on the sigma algebra, so it's assigning probabilities to sets. And it has the following properties. It's normalized. Which means here that there's also a typo. P empty set is 0 and P full set or omega outcome set is 1. So this is kind of this applies to probability theory. In measure theory, one doesn't need this normalization thing. So that's a thing specific for probability theory. And P is what is called sigma additive. Which means if you have a pairwise disjoint sequence in A, so you have countable many sets A1, A2 in A, and they are pairwise disjoint, so they don't overlap. So if you think again in terms of these kind of Venn diagrams, if this is omega and you have a set A1 here and another set A2 here, they don't share any elements. If you have another set here like this, then they obviously overlap. So this is not what is considered here. Here is only the case of pairwise disjoint sets. So the intersection of these sets, of all pairwise intersections, is always the empty set. Then the probability measure of this countable union is the sum of the individual measures. So, and that is called sigma additivity. So this is kind of, this is not kind of, this is the abstract formal definition of a probability space. One can do certain things here and there a little bit different, but the important thing is that a probability space always comprises this elementary outcome set, then a sigma algebra defined over this elementary outcome set, and a probability measure, which is a measure, which is a function that assigns values between 0 and 1 to the sets in the sigma algebra. That's a very general thing, and this is a very general model. And in mathematics, one now studies, the implications of these definitions and how they relate and so on. What we will do next, to make this obviously more concrete, is to discuss a specific example. And this is kind of the typical example that's always discussed. There are two typical examples always discussed with respect to probability spaces. One is tossing a coin, the other one is throwing a die. And we will do the second one. So to give some meaning and some life to this and discussing of what it's meant. So this is an abstract model. It's like the GLM without talking about what the conditions are and what the beta parameters mean in a specific experiment, and without having observed data. It's kind of a very abstract thing, and it doesn't really have meaning on its own. It only has power in the sense that you can assign now things to it and make it more concrete. So let's make it more concrete. And now we discussed the notion of a probability space for modeling a random experiment, which one might call the die experiment. Never sure whether it's die or dice. Also from the, so Mark, you're a native speaker. Would you call it a die experiment or dice experiment if it's only one die?
One die.
One die, okay. We call it a die experiment. Good, so we have one die. And as you will figure, if you throw a die, one single die, the whole setup is that one of 6 things can happen, namely one of the sides which has this pips, I think as they are called, so these kind of things on a die. One of these things will come up. Yeah? So in terms of a probability space, what one can do many things. The probability space just says omega is a set, but the typical, so let's first write down that we have this. Omega is a set, so essentially we could also use a set in which we put these pips. So one could define a set of things that look like this, because sets are fairly general, they don't have to be numbers. So one could do a set like that, but of course in applied mathematics it's always easier to deal with numbers. So we come up with a set of 6 numbers, 6 integers, 1, 2, 3, 4, 5, 6, which we can also of course call the natural numbers up to 6. Yeah? So this is now our elementary outcome space. So the entries of this, you could, if you want, you can call omega 1 is 1 or something. These are the elementary outcomes. Yeah. So let's keep it like that. That's fairly clear. One thing that you might also realize from the setup is that if you use a probability space to model a random experiment, then you always have with it the idea that you can obtain realizations of the elementary outcomes. Yeah? So for a die, you can throw it, and then maybe this thing comes up, and then you would say, okay, on this occasion of the elementary outcome, this realization of the random experiment, the elementary outcome omega that was realized was 4. Yeah, so these are the elementary outcomes that can be realized. Questions about the elementary outcome space at this point? No. The bigger problem, I agree, is the sigma algebra. But for the sigma algebra, there is a simple thing that I, at this point, internalized, which helps me to get through some of the mathematical probability theory, is that instead of starting to think of sigma algebras, you think about power sets. Yeah? So we define, and in the discrete case, this is completely sensible and makes a lot of sense, and it's also fine mathematically. So we define the sigma algebra as the power set of omega, where with the power set we mean the set of all subsets of omega. So that's really what a power set means. And the good thing is, if your original set from which you can evaluate the power set is not too large, then you actually can write everything down. So I don't want to do it now for the set with 6 entries. Let's go for a smaller one. Let's say our omega, just as a side note, is has just 1 and 4. Then the set of all possible subsets, so the power set of this small omega is contains the empty set, because the empty set is always in the power set. It contains the full set, because the full set is always a subset of the original set, and then it contains the set that contains only one of them. This one and both of them, which is already omega. Yeah, so I hope I didn't forget anything. Is there another subset? No.
It doesn't matter in which order.
No, orders don't matter for sets. Basically, what you are up to is whether this and this are different sets. No, they are the same set, but it's a valid point. So this is the power set, and of course you can write down the power set for 6 as well. Now, why is that being done? This is being done for the mere reason that you want to, in a random experiment, you want to be able to talk about something called events. So the elements of, the sets that are in the sigma algebra, they are called events. And this derives from the desire to, if you throw a die, you want to talk about the probability of it coming up, for example, 4 or 5 or 6. And then you can define something, and then you say, okay, that's 1/6. But you might also be interested in another event. For example, the event that the number that comes up when you throw the die, or the number of pips, is smaller than 4. Yeah. So, for example, you can talk about the event that the realization is one of the pips smaller than 4. And then you can think about, okay, what does that mean in terms of a subset of omega? Well, 1, 2, 3 is the event that, so it's a subset of the outcome set, is the event that the number is smaller than 4. You can also ask for the event is that what is the probability that the number that comes up, the number of pips that comes up, is even. And then you can say, okay, that's the subset 2, 4, 6. Yeah. Or what is the probability that the number that comes up is larger than 4 and smaller than 2. So that would be the event. So larger than 4, that would be 4 and 5, and smaller than 2 would be 1. Yeah. So with this power set, so with allowing every possible subset of the original set, you basically cover all of the events that some interested master students would be willing to know the probability from, or anyone would know the probability from. So you can frame that differently. You can also say you cannot formalize an event when throwing a single die that is not in the power set. So you can even describe a probability for the event that the die shows anything. So what is the probability that the die shows anything? So any number between from 1 to 6, well, that's the probability of the whole outcome space, and that's always 1. So the probability that something will happen, something very unspecified will happen, is 1. At least in the model of the probability space. And you can also model the fact that you throw the die, but it rolls off the table and you will never see it again. So that's essentially the probability that nothing happens. And the probability that nothing happens is 0. For the last two things, actually, you see the model assumptions, because these are really model assumptions, because the probability that the die, so that nothing happens, that the die disappears. From everyone who played games, they will have made the experience that this actually happens. This shows that this probability space model is not an optimal model for really for real die experiments, because so for the actually physical realization, because these impossible events that should have a probability of 0, they actually happen. Yeah, so that's kind of a mismatch. So these are definitions and axioms. Yeah, so the whole thing is a model. It's not about the real thing. Good. Maybe let me do one more thing, and then we take a break, because then we already have dealt with this thing. There was the notion of a probability measure, and we haven't talked much about this so far in the die experiment. So one can show mathematically, whatever that should mean, that the definition of a probability measure entails that it assigns a probability to the elementary outcomes. For the die experiment, the natural fair die probability that you have in mind is, of course, that the probability for seeing 1, for probability for seeing 2, and so on, is, in the case of a fair die, is 1/6. This is, of course, in a probability space, that is a definition. This is something that you, when you say, I'm defining a probability space, omega is my set, R is my sigma algebra, here take the power set. Now I define a probability measure. You have to, of course, say how you now allocate probabilities to your events in your sigma algebra. The other thing that is said about a probability measure in the definition of a probability space is that it's sigma additive. So if you have disjoint events, then the probability of the union equals the sum of the individual probabilities. Let's see that for an event, for example, maybe for the event that the number that you see is an odd number. So what would be the subset of our sigma algebra for that we are interested in when we are interested in the event that we are looking at an odd number?
135.
Exactly. So that's our event, which is an event, of course, in our sigma algebra. Oops, sorry. In our sigma algebra, because all events are in our sigma algebra. And as you might be able to infer, is that you can create this event by the union of five, I'm just writing 5 down, of 3 other sets in the sigma algebra, and these sets are mutually exclusive. So in the set 1 there is no 3 and there is no 5. In the set 3 there is no 1 and there is no 5. In the set 5 there is no 3 and there is no 1. And what this sigma additivity then says is that the probability that is assigned to this set 1, 3, 5 should be the sum, or not should be, but is the sum of the probability assigned to each individual event. And this, if you define it that you have a fair die, this is then 1/6 plus 1/6 plus 1/6, so that's 3/6, and this is 1/2. Intuitively, this is very sensible because there are 50% or there are 50% even numbers on the die and there are 50% odd numbers on the die. Now, if you throw it, the probability for an even or for an odd number is, of course, 0.5. So it makes sense that the probability for the event that an odd number shows up is 1/2. Yeah. So this is, for this example with the die, an idea about the sigma additivity, you saw that we have this infinity there, so it's countable, but it doesn't always mean that it needs to go to infinity. If you are dealing with discrete and finite sets, then it's fine to end this union at a finite number. Yeah? So this is just the most general case that people wanted to push the definition so that limits where you sometimes need to go to infinity makes sense. Okay, so let's say that we discussed one example for a probability space now, and this is only one example. There are millions of examples around the world for probability spaces, so I appreciate that it's not completely clear what the power of the definition is, but at least we've seen one example. We take a break now, and then we discuss a little bit more about probability spaces and then random variables. If there are no questions right now. No. Good, then let's take a break.